So kind of the plan today, well, as the slide says, it's security and Pi, and the Pi is like a shout out to Android 9, which came out, which is, of course, Pi, as they give a clever name to every release. And my goal is for this talk is like we're really going to start at the hardware, and I think everyone here probably has a little mobile phone, and just work backwards from like the hardware, or I guess that's forwards, from hardware to the Android OS up into a Play Store and then to a regular application. And the only slide that I'm going to talk about myself is this one, so don't worry. We're not going to do it a lot. And I, of course, picked a photo with me with a donkey because it makes you look at it. I'm a senior software engineer at SourceToad. A couple of my employees are here, so thank you for supporting me. I'm also the APK Tool maintainer. It's a little open source tool that's the only open source free tool for decompiling and rebuilding Android apps. Since the time is all out of whack today, I'm going to go pretty fast. And if you guys want to get out of here because I'm going over, that's fine. Bunch of social stuff if you want to check it out. But kind of the background on things is there's too many mobile devices. And what we learned at Google I/O in 2017 is Google has 2 billion monthly devices. And that's a pretty huge number. And this makes it a big target. There was a joke I remember that was like, why are a lot of viruses on Windows? And it was because they had a huge market share. And likewise with Android, the more people you have, the more you're targeted. And CVEs are a good indication of that. It's basically vulnerabilities that are exposed, and you can see it's pretty much exploded. And whether this was Android actually taking security a bit more seriously and stepping it up, or more people were targeting, you don't really know. And my 2018 data isn't the best because that information wasn't out yet when I was finishing this slide deck. So maybe the graphs will look similar. I don't know. The mobile world has definitely changed a lot because people are doing too many things on their mobile applications. You guys might be doing banking, mobiles, medical things. You probably have two-factor auth from a variety of places on your phone. And you might use it to actually get into your hotel room. I unlocked my hotel room door with my phone, which is a bit alarming because if I can unlock my door, whose else's can I unlock? I hope just mine. Not yet, but it might be fun. So of course, we're going to start at the hardware, and there's too many companies, way too many of them. And I think you might recognize a few of them here. One thing that I think everyone would probably know is the Snapdragon from Qualcomm. You hear it in the news a lot because they're probably the largest media blitzing one. But these are all great. Not really great ones, but they're out there. Today, I'm just going to talk about the Snapdragon. Everyone knows it. And they have something that's really probably leading edge in the security. And they have a bunch of cool 3-letter, 4-letter things. And it's a SPU, or a secure processing unit, which imagine on a chip is like this really isolated RAM, CPU power, vault-like thing that you put secrets and credentials into. And things can't break into it because it's kind of isolated outside. Likewise, instead of like a storage area, they have a TEE. It's actually prefixed with a Q for Qualcomm since they had to prefix it. But I'll just put TEE up here for Trusted Execution Environment. And this is basically, as it says, a high-level operating system where you can execute code in a trusted manner. And that's really what new Android devices are coming with. Like the idea of this is like if you're going to sign something on behalf of something medical, it's going to launch you into a TEE mode on your Android device, which is like a really protected approval screen that no apps can intercept or malware. That's pretty nerdy, so I don't want to talk about hardware anymore. So move on to Android, which is a bit more fun. The Android platform's huge, a bunch of categories, and we're going to hit all of these really quickly because we're low on time and just go through them all. And this is just encryption, sandboxing, and there's a beautiful report Android does every year. Unfortunately, the 2018 one wasn't out, so I did the last year. To start with is this cool little thing of a security patch, and Android does it every month now. And you can kind of tell if your provider is good or bad based on what security patch you're at. And this is just something that comes out every month with everything patched that has happened at the kernel and Android. So you can open up your phone, go to settings, and look at your last security patch level. This is, of course, Android people only. OEMs try and follow this pretty well. Most of them suck at doing it, and they're 6 or 7 months behind, but some are really good at it. One quick slide about an Android booting up is the very first thing your phone does when it turns on is it has to boot into Android. But that process can be intercepted and modified. So this is where Android verified boot comes in, which basically checks the entire boot sequence before it starts to make sure what you're executing is clean. A lot of people actually hate this because when they want to modify their phone or do something, they have to work around some things in order to boot their own software. But it's more so for the daily use person who wants to confirm that their Android device is secure every time they turn it on, and something malicious hasn't, unbeknownst to them, taken over. So my first really nerd deep dive into something it's called ASLR, and someone here might know it, and no, it's not ASMR, it's ASLR. And for this example here, I'm just gonna try and show you that, imagine these are just a bunch of hex addresses on the side. Like memory holds things, whether that's secrets or your app running. And for some example, we wanna get this red secrets blob. So what we would do is we would target the application that's running and try and get it to overflow. And this is just finding a vulnerability, anything we can do. And since we know where the secrets are, well, we don't really. We pretend we know who they are. And we want to read that block of memory for secrets. So our goal is just to continue attacking this application until we can read that little blob. And before ASLR, it was pretty easy because the memory location of secrets never changed. Now what ASLR is actually address space layout randomization, which basically means, in that very nerdy word, is the locations of things changes on every boot. Because computers are very bad at doing random. A computer turns on, it does the same thing every time, which puts it in the same memory every time. That is different now. ASLR basically puts everything in a different location. So one attack you successfully do on one boot won't work the next time because the things you're doing is moved. And this is what Android 9, which we'll see here, has done. So I'm gonna click between these really quick because it's impossible to read this and have any idea what's going on. But you can barely see if you're looking at that top two, like you can see the numbers are barely changing. And that's actually huge because a hex address on a real device is not gonna be one letter like I had back here. It's gonna be a much longer string. So that's ASLR in real world, which it just makes it more difficult to find entry points to attack things because they're constantly moving locations on every boot. So you may attack one device, but it's not gonna work on another, unless you, of course, can find a way to automate that, which is why attacks are becoming much more hooked together and crazy. On top of this is something called DEP, which stands for Data Execution Prevention, and that's basically the idea that you have a stack of activity going on, or kind of how your computer works at a very low level. And DEP says you can't execute anything on that because your computer jumps around and then does things. It's not supposed to execute the code when it's moving around. That really jumps in with ASLR, but ASLR at the end of the day is just going to randomize everything. I put a big list here, but we don't need to worry about that. It's more or less most of the system. Going to something that's also very nerdy is Android SELinux. Stands for Security Enhanced. A lot of people maybe not know that the NSA started this and actually contributed it back to the kernel in the open source space. It's pretty cool. It's also very annoying, but it's basically the protection of information. A program process something has to ask for a privilege to get access to something. And we're gonna look at a quick overview of Android of what that meant. And it happened way back in Android 4.3 where they added SELinux but didn't enforce it. And that's called the permissive mode, where basically anytime something happened that wasn't allowed, it just warned in the error logs about it. And then you can see gradually it got more enforcive, and then they patched more and more things. If you see down there with media server, the name Stagefright might ring a bell, and that was a pretty bad media vulnerability that happened on Android, and that's where SELinux came in to help it. So where Android 9 comes in, finally, after this many slides, they added per-app sandboxing for SELinux, which basically is your application running in its own container. This is a big deal because in the past, people have been leaking content providers. And this was something as simple as you make something which you think is easy in your app to put data in, database, text message, et cetera. And someone can make a malicious app that literally only targets your app to extract info. This is really not doable anymore, but if you still need to share data, content providers is your thing. Moving on to encryption. This one's a pretty easy one to talk about because what happened in the past was just like a full disk encryption, where your entire Android device at boot was encrypted. I mean, you were decrypting it with one key. This is annoying though, because how does your Android phone work if it's off or turning on. It has like a subset of functions until you enter a password or passphrase, a little drawing symbol, whatever. Now it's file-based, and with the new Android coming out, metadata-based. And metadata-based, we will skip this, is kind of everything else that you think that happens on a file system, which is your permissions, creation, and how big a file is, which you think means nothing, but you can determine a lot by what a file is based on its size and creation date. This is protected in Keymaster, but without throwing a lot of terms at you, you can ignore that for now until we get to it. But now it's time. Keymaster is this great thing we're going to look at, which has grown over the years, and we don't have to worry about what all this means, but the idea is that there's this block of code, location on your Android device, which goes back way back to that hardware section, where you can store secrets. And this might be anything that is re-authing itself behind the scenes, probably is storing something in a location. And this started off just as access controls, which isn't very good, so it moved to version binding, which basically meant if you made a secret on Android 4.4 and someone attacked your devices and extracted that key and tried to run it on an Android 4.3 device where they knew a vulnerability, they couldn't do that because the key was directly binded to the version. And you can take that same thinking with the ID version because it also applies to your serial device of your device, your IMEI, and that just means that you can't take someone's updated Android device, extract the secrets, put it on your device, and then try and take them because you won't be able to decrypt them because you don't match. Strongbox. This one we're going to go into, which basically ups all the security even more, and you'll see this came in Android 9. And I Googled Strongbox and found this. I don't know what makes it a strong box, but it looks pretty strong. But that's not what we're talking about. It's just a separate CPU, and it goes back to the hardware things where you can have a true random, tamper-resistant little area to do work. And that's great because you need somewhere to mess with secrets, because if mobile phones are going to be used more and more often, you need to have something secure in them to do things that you really care about, whether that's banking or medical-related things. This one is going to be tough to explain, so I made a graphic we're going to look at. CFI stands for Control Flow Integrity, and it's a big, big, crazy, complicated thing to look at. Almost as complicated as ASLR, but we're going to try to explain it. The little quote here, 86% of vulnerabilities in 2016 were memory-related. This is going to continue to be a problem in everything, and that's because memory is a dangerous area. And to explain this, we get to look at a cool drawing I made. Pretend you're logging into a website. There's two flows. You basically log in or you don't. You miss the password, you have to retry, or you log in and you're redirected to wherever you're intended to go. What happens in a memory attack is someone comes along and they want to do their own block or their own path of execution, and that's this little hacker guy. I imagine that's what a hacker would look like if he was hacking my Android phone. But where CFI comes in is CFI knows how your program works. During build time, it comes around and like enumerates every possible path that your code can do. So it knows what happens when it fails, it knows what happens when it succeeds, and it knows the paths the code has to take. So what happens when this attacker comes in and tries to execute their own code is it works outside the bounds that CFI knew about at build time. So CFI sits here and says, oh, I'm not going to allow that code to run, and rejects it. The problem with this is it's very difficult to implement CFI, which is why it took Android all this time to do it. Because if you have shared libraries and you have to do this at build time, it just takes a while. Now that Android has been refactored at such the low level so many times, it is now enabled in 9.0 in your components and kernel, which is a pretty big deal. The Stagefright attack, if you remember, allowed someone to send you an MMS image that would basically take over your phone. That's really not possible with CFI anymore, assuming that you're on an Android provider that has enabled this security benefit. So, ending this little section of the Android platform is just a bunch of really nerdy things, from protection of data, that was our Strongbox, all the way to the kernel, which can protect itself with memory locations and CFI. And then verified boot, we really didn't talk about much. We skimmed over that slide, but It just basically means, hey, am I booting a secure Android? This is my favorite section of the talk, and it's the Google Play Store, because Googlers around probably refer to a lot of things as PHAs, which are potentially harmful apps. And those aren't good at all, because people lose trust in a Play Store and App Store when there's viruses on them or anything harmful. So Google Play Protect is really what it's marketed as, and it can find your device, which is really helpful, block bad websites. It's that big red bar you've probably seen. But really what its main point is it can detect and remove PHAs from your Android device automatically. Some would say that's probably an invasion of, I want a virus on my phone, so leave it sort of thing. But it's very powerful, and we're gonna look at why that is. Yeah, so we just talked about it, PHA. One of the big things is the fraud purpose, and I don't understand still what premium messaging is or why anyone would want it. But fraud is the big deal these days of someone can take control of your Android device, text a few numbers, and they pull a couple dollars. In the masses, that's a lot of money. So that goes back to I still have no idea why premium messaging exists. A bunch of other bad things are PHAs, but we're just going to look at fraud. So a big list here. It's funny, I didn't know how to pronounce this first word here until I saw a YouTube video with a Googler, and he pronounced it Shammi. I have no idea how you say Shammi from that, but maybe he's right, and maybe he is, so we're going to talk about that one. But Shammi is the biggest SMS fraud and botnet that was found in 2017, and it basically pieced together a bunch of bad Android things to work, which made you visit pages that were just full of ads behind the scenes. It basically sat in the background and waited till your phone was inactive, so it knew you weren't using it, would view web pages and then get rid of it without you knowing. It installed apps automatically. That doesn't seem pretty hidden. I would notice if there was an app on my phone. But the big deal is that SMS fraud with the premium texts, which are very stupid. The whole reason behind this and how Google blocked it is SafetyNet. And SafetyNet could be a talk on its own. You could probably sit here for an hour and discuss it, but we're going to do it in about 3 minutes. It's marketed by Google as Verify Apps API or Google Play Protect. You see it in the little top bar when you're updating apps probably. It sits there, a little spinning around. But the brains behind it is SafetyNet. And we're going to learn what that is real quick. There's a guy, John, I'm not going to pronounce his last name since it looks like Krasinski from The Office, but I don't think it's that way. He's been researching SafetyNet for years and blogs about it all the time. His domain's so easy, so cause.io if you need to. But for us to investigate SafetyNet, we need to download it. So there's a cool little script, GitHub link in the bottom there with a little bit.ly link that's cut off. You basically can download the binary. And this thing updates way too often, which is why there's a script to download the latest. Investigating this thing a year ago, maybe 2 years ago, was so easy. Now it's pretty difficult. It's obfuscated now, and it's been moving into more and more complex styles of code, which make reverse engineering it, very tough. But what this does is it runs with permissions that most Android apps don't have because it runs under Google Mobile Services, which is like a higher level grant than you could get as an application developer. It's huge, it's complex, it's module based, and I think most of the information that this thing harvests goes back to some machine learning thing at Google. And we're going to take a look at what it harvests. There's a huge list here. I'm not going to talk about them all. You can kind of infer what it means by the name of them. And the module, for example, called SU files, basically looks on your Android device if it can find the SU bin or binary on your phone. If you have that, you basically are a rooted phone. Why Google wants to know that is basically if you're going to use a bank app, they want to confirm your device is trusted. If you try and use Android Pay with a rooted device, probably doesn't work. And likewise, the biggest named game to do this was Pokemon Go. They required you to have a valid device from SafetyNet to play. A cool list here, like SSL Handshake was a great check to see if you're being man-in-the-middle attacked. It would basically visit a website and check the leaf certificates to make sure. And a bunch of other ones here. And this list is actually only page 1 of 2. There's a bunch of them. It would take forever, as I said, to go through all these, but just know that SafetyNet is this huge modular thing running on everyone's Android device, learning about how your device works and whether it's in a clean or dirty state. So like I said, we talked about a few of them. MX Record's a cool one as well because mail fraud is becoming pretty common these days. JavaScript injection really happens at the the carrier level, like your ISP. It's a very dirty technique that they'll actually inject JavaScript into every single packet your computer sends to put something on a web page. Thankfully, with HTTPS, this is becoming more difficult, but also your ISP can change your SSL certificate because they are, of course, your network provider. So a lot of cool checks in here. One interesting thing about SafetyNet, though, is inside of it is another portion called Droid Guard. And it is this huge native blob of, I just call it magic, because it's tough to reverse engineer, shorthand RE, and it grows with features every time this thing updates. And no one knows what this thing is really about because it's impossible to reverse engineer. And by the time you finally get a hold of what it's doing, 10 updates have come out since then. This thing does some crazy things. It sits in the background, and it learns about your device when you're not using it. Because some people have the idea that like SafetyNet works by you click a button, it sends a request, it checks your phone. Not really. This thing runs all the time on your phone every single day, just learning how your device works. So at any time, if someone wants to request from SafetyNet the status of your device, it knows. So the final little bit as we're flying through this is the application itself, now that we've looked at the hardware, Android, and the Play Store. An APK file is literally a zip file. You can unzip them on your computer if you want. You can just download an APK and unzip it. It really won't help, though, because you're going to get these files called DEX and ASRC, which aren't exactly human readable in any way. But thankfully, I make a tool that's called APK Tool, and you can APK it right back to a semi-readable human source, which gives you the res folder in Somali, which is like a Jasmine style of bytecode for Java source of applications. There's a cool command you might know called file. It basically reads the magic of a file and then tells you what it is. So you can see the very first one there, app, is just me, I unzipped a file. The second one is me APK tooling an application to source, and it basically reads out, boom, it found an XML document, but the first one was binary XML. It's very easy to read raw XML versus looking at binary XML, unless you're a computer sitting here, in which case you'd probably prefer the binary. So jumping along from that, I have to market my little free open source engineering tool. It's on GitHub. You just literally search APK Tool. Been doing this thing now for 9, I think almost 10 years now. And it's stressful, but a fun open source project. Need all the help I can get if anyone's really into Java, because there are too many bugs to keep with this thing. I think we have over 100 in the tracker, and there's no end in sight. So as I talked about, we looked at a DEX file and talked about it briefly. It's like the source, like that Java you write, or Kotlin these days. And ARSC is like the compiled version of all your strings, layouts, and any themes you have in an application. And of course, a libs folder for any game engine you use or library, and res for all your images and anything that's raw, like audio or random files that you might have in your application. So as we finish up here, APK signatures was a pretty big deal. We had one, which was just like a manifest signature or a jar signature for years. I mean, it took until Android 7.0 till we got a new one, which was called the APK signature block v2. But what happened there in the question marks in the middle is we had some really bad bugs, and people blogged about them all the time because they basically meant we can take an example. One is you could put the same file in a zip file because nothing in the zip file spec says you can't have the same file twice. But Android verifies the first file but loads the second, which is a very scary thing, which meant you could put a bad file in it, name it the same thing, but put it after a clean file. And Android would load and verify the clean but execute the malicious. And that led to basically the invention of the signature block, which instead of a signature of a jar file became this huge block of a big binary blob of all this information you see, which made it a lot more difficult to maliciously edit. So cutting it back to Android 9 is they came out with this v3. And don't worry, we're almost done. to speed through this is Android 9 basically said, hey, what's happening is companies are buying other companies all the time, and there's this awkward stage where they basically have to release an app that tells you to download another app, or they have to just release a new app because the old company is not giving up their private key, and the new company can't republish the app on the same one. So now Android 9 has this idea of a key rotation, where the old company can release an app update that have both private keys of the company to then let the new company take over. Unfortunately, though, like everything Android, everyone has to be on the new version to benefit it, so this probably won't be helpful for another 3, 4, 2 years. So with that, we are definitely closing the last slides here as we fired through this. As Android is scary. I mean, anything online is scary. Internet is scary. Security makes me nervous. And I basically want to say, please, please take those updates on your phone every month if they exist. If your carrier doesn't give them to you, then I would switch phones and find someone who updates their phone within 3 months. Please download apps from the Play Store. If you have that little checkbox unchecked because you download apps from freegames.com, then don't do that. A big source of bad things, and of course, leave those slow OEMs behind. I have a OnePlus phone. They were great. Now I'm not so sure anymore. So I don't know where I'm going to move to next, but if you're going to trust your whole life in your mobile phone, you probably have to be with a company that respects it. I fired through that, and we are done. So thank you for staying, everyone, and that was it.